All right, welcome back. It's been a little while, but here we are, and we're going to be moving into a new chapter, chapter 22. So what we're going to be looking at now are something called carboxylic acids and their derivatives. So to start off, a carboxylic acid is an organic acid. So we've seen these before. And my pen thickness is a little too much. There we go. And this is our so-called carboxylic acid. And as we've seen before, it contains an acidic proton. And carboxylic acids are not terribly strong acids. In fact, they're not considered strong acids at all. They typically have pKa values in the range of around 5. And depending on what the R group is, that value can go as low as 0, actually, I've seen. But typically, if you don't have anything fancy on your R group, we typically are just looking at around a pKa of 5. So the carboxylic acid derivatives which we're going to go ahead and call CAD for short. By definition, these are any organic compound that can be hydrolyzed to give a carboxylic acid. So when we say hydrolysis gives carboxylic acid, then we're talking about a CAD. Right, so when you have a molecule and you hydrolyze it and you get a carboxylic acid, that is a CAD. Right, so what we're going to look at first, an example, is something called an acid chloride. All right, and this name's a little bit confusing because it's technically not a Bronsted acid. It is just derived from an acid. A carboxylic acid. So the way they've kind of gotten around that confusing terminology is something called an acyl chloride. And I'll be honest, I don't use that term as often. I call them acid chlorides still. So you need to be familiar with both of those terms. So an acyl chloride or an acid chloride has the following structure. Now you can see the acyl group and it's attached to a chlorine, so that's why it's called an acyl chloride, and that's actually quite an easy name to use. If you were to react this with water, we get a hydrolysis reaction, which literally means breaking bonds by water, to get our acid plus a molecule of HCl. So by definition, the acid chloride is a carboxylic acid derivative. So here is our acid, and this guy over here is our CAD. All right, so that's how we can define something as being a CAD. That hydrolysis gives the carboxylic acid. So what we're going to do is we're going to look at examples of CADs that we're going to discuss in this course. One that we just saw was the acyl chloride. Right? There is also the anhydride, which looks really weird, but it is also a CAD, and we'll look at reactions of those. So this is, of course, the acyl chloride. This is the anhydride. We're also going to look at something called the ester that we've seen before in infrared. And the amide. All right, the nitrogen can have either R groups or hydrogen, and that'll give us different types of amides, primary, secondary, and so forth. And finally, one that doesn't look like the others is the nitrile. All right, so if we look at all these CADs, they all have what we would consider a carbonyl group. All right, that's the C double bond O in each case, so I'm going to highlight that with red. However, the nitrile does not have that, all right? And something else that you may be noticing is missing from these groups are the aldehydes and ketones that we just discussed last chapter. Those are technically not considered carboxylic acid derivatives because hydrolysis does not occur in ketones or aldehydes. We actually get hydration, all right, but we do not get hydrolysis. So we do not consider those to be carboxylic acid derivatives. So what I want to do next is go through and look at the reactions that these carboxylic acid derivatives undergo, all right? And it's a little bit repetitive because they all undergo these reactions. So we'll just pick an example. We'll say, all right, we're going to do this reaction on an ester, or we're going to do this reaction on an acid chloride, so forth. But for the most part, these reactions are all going to behave the same on these carboxylic acid derivatives, save for the nitrile. All right, the nitriles is going to be a little bit different because, as you can imagine, it does not contain that carbonyl group. So we'll look at the nitrile on its own towards the end. So types of reactions that we're going to look at is going to be nucleophilic addition, elimination. Let me try this again. So this is a two-step reaction, so it's hyphenated, all right? We get nucleophilic addition like we saw with the addition of a nucleophile to a ketone, for example, but now we get a subsequent step that we didn't see earlier with the ketones that we call an elimination, all right? So what I'm going to do is I'm going to take a generic carboxylic acid derivative here. So rather than say, all right, this is an acid chloride or this is an ester, I'm going to say this is a generic CAD. In the Y group, all right, this is what we're going to call our leaving group. So if we go back to these carboxylic acid derivatives, can you tell me what the leaving groups are in each case? All right, so basically we're just trying to figure out what the heck Y is. So in blue, I'm going to go ahead and circle them. Okay, chlorine is our leaving group there. All right, now the anhydride may be a little bit trickier, right, because it's big. But let's just skip ahead to the ester to see if we can figure it out. All right, so notice what we circled for the acid chloride. We just took the chlorine that was adjacent to the ACl group. You do the same thing here. So the ester, the OR is the leaving group. And in the case of the amide, the nitrogen is the leaving group. So how are we going to deal with the anhydride? Well, we just have to make a big circle. All right, these are the leaving groups for the carboxylic acid derivatives. And in the case of the nitrile, it's probably a little bit hard to see, but it is the nitrogen itself as well. All right. So those are the leaving groups, or what we're going to call the Y groups. Now, this doesn't really fit the nitrile, right, because we don't have a carbonyl. But as I said, we're going to deal with that guy later. All right, so this is our leaving group. And I'm going to go ahead and erase this now. So when a nucleophile comes in, let's say it's negatively charged. So let's say the nucleophile is negatively charged. Well, nucleophilic addition, we've already seen this with aldehydes and ketones. It's not going to be anything new. All right, so we add to the carbonyl carbon as we've seen before. And then there's our nucleophile. All right. So what happens? Well, we've done the addition step, and next is the elimination step. So if you remember elimination from the first semester, we were talking about E2 and E1 reactions that ended up forming CC double bonds. That's kind of what we're talking about here. We're going to not form a CC double bond, but we're going to form a CO double bond. All right. So what's going to happen is the oxygen is going to collapse. All right, and it's going to reform that CO double bond, and it's going to be able to kick out two groups. All right, it's either going to kick out the Y group or the nucleophile. All right, and if it happens to kick out the nucleophile, well, the reaction just goes in reverse, correct? However, if it kicks off the Y group, the reaction is going to go forward. All right, so we lose Y minus. So my question is, well, why would this reaction ever go forward? right, or in the forward direction, why would it, or would it go in the reverse direction? Well, which direction is going to go? If there's something you've heard me said several times before, it's that equilibrium always favors the formation of the weaker base. So, which one is the weaker base? Well, the question is the weaker base going to be the nucleophile? Pardon me, that should have its negative charge associated with it. Right? Is the weaker base the nucleophile, or is the weaker base Y minus? Well, that question is impossible to answer right now because we don't know what the nucleophile was or what Y minus is. All right? But we've spent enough time looking at bases and their strengths to figure out, well, what's a good leaving group? All right? What's a weak base? So let's take a look at a reaction. All right? Let's take a look at an acid chloride. Not an acid chloride, sorry. And let's react it with hydroxide. Now, going back here, what was the question we had to ask ourselves? What is the weaker base, the nucleophile or the leaving group? All right, so here we're looking at hydroxide. All right, hydroxide we know is a what? Strong base. So this kind of sounds good for us, right? But let's just be complete. So what we're going to see is addition. Followed by elimination. So if we want this one to go forward, who are we going to kick off? We're going to kick off chloride. All right, so who are we trying to compare here? We're going to try to compare hydroxide, and we're going to compare chloride. All right, well, which one's the stronger base? Hopefully you guessed that the stronger base is hydroxide, and chloride is an extremely weak base, right? Because it's conjugate acid, hydrogen chloride, or HCl, is a strong acid, so chloride is a weak base. So which way does the equilibrium favor in this reaction? It's going to go all the way towards the products, all right? Heavily favored towards the products. So this is a good reaction, all right? How about if it was in a different, we look at a different scenario. Let's take a look at an ester. All right, so our leaving group in the case of the ester is the OR, all right? So we kind of need to talk about pKa values again. Because if we look at the leaving group, right, we need to figure out, is this a weak base or a strong base? Well, its conjugate acid has a pKa of around 17, all right? So this is a what? Weak acid. Thus, this is a strong base, all right? So the OR minus is not a very good leaving group, all right? However, ROH is a good leaving group, all right, because it is a weak acid, all right? So weak acids are good leaving groups. Weak bases are good leaving groups. Strong bases and strong acids are terrible leaving groups, all right? So we need to figure out, well, how can we make this a good leaving group? Well, there's another way we can do addition elimination. In acid catalyst. All right, so this will be good for systems that have poor leaving groups like esters and amides. So let's take an ester. And we're going to add acid. And we'll use water as our nucleophile. So in the first step, what we have to do is activate the carbonyl group, just like we did when we had acid-catalyzed addition to aldehydes or ketones. So we'll protonate the oxygen in the ester. And now we have water, which is going to be our nucleophile that will attack and deposit the electrons up onto oxygen. So now what I'm going to do is I'm going to move on to the next slide, and I'm going to draw our tetrahedral intermediate, or our resultant intermediate from this reaction. So we're adding an O to that carbon. So our new tetrahedral intermediate, make sure I get all the oxygens in the right place. All right, so this is our tetrahedral intermediate. And as I've said before, if you have a tetrahedral intermediate in acid, the only way you can have a leaving group is if that leaving group is protonated. All right, so if our protonated oxygen on kind of the southern hemisphere of this molecule leaves, then we go in reverse. All right, so that's not what we want. We want to go forward. So what we can do is we can do something called a proton transfer, where we steal the proton from a neighboring group that's protonated. So now we have a group that's protonated, and the oxygen can collapse back down and kick off that oxygen. Water's still floating around. And we just kicked off ROH. Now remember, I said OR minus, or sorry, RO minus, pardon me. RO minus was a terrible leaving group because it was a strong base, but its conjugate acid, ROH, is a good leaving group. So we just kicked out a good leaving group, all right? And to complete this reaction, we're going to regenerate our acid by creating the neutral organic product. And there's our carboxylic acid, all right? Plus H3O plus and ROH. All right, so you can see that it's catalytic. There's our regeneration of H3O plus. All right, so technically this was a hydrolysis of an ester. So what we've seen thus far is the addition elimination reaction in acid catalyst, and we saw the addition reaction, or sorry, the addition elimination reaction under basic or neutral conditions. All right. So we could go through each one of these and give you an example of every reaction, but it's a little bit repetitive, and you'll get some practice at doing it. But what we need to be able to do is rank these carboxylic acid derivatives and figure out who are the most reactive in these nucleophilic addition elimination reactions. And it all comes based off of their leaving group. So there we have the acid chloride. Here we're going to have the anhydride. Then we have the ester. And then the amide. All right. What did I do there? Filling in all my lone pairs here. Okay, so now my question is, can we make a table, the leaving group, and then the pKa of conjugate acid? So the leaving group here is chloride. All right, the pKa of its conjugate acid. So the conjugate acid of chloride is HCl, all right? And that is around -7. So my question is HCl a strong acid? Yes, it is. Does that make chloride a good leaving group, or better question, does it make it a weak base? And yes, so this is the best leaving group, all right? And you will see this trend emerging. So the leaving group here on the anhydride is there, all right? So this is called a carboxylate, all right? So it's the conjugate base of a carboxylic acid. So the conjugate acid of the carboxylate is a carboxylic acid, where we said that pKa value is around 5, all right? So it is considerably weaker acid than HCl. So the leaving group is nowhere near as good, but it's still decent, all right? Because what we have here is a strong acid and a relatively strong acid at 5, all right? So the leaving group for the jumping ahead. The ester is what we call the alkoxy group, all right? So the alkoxy group we should recognize as a strong base, all right? The alkoxy group's conjugate acid is an alcohol, and alcohols have pKa values somewhere around 17, all right? And these are approximate. It really depends on the nature of R, but 17 is a safe number, all right? So that is a considerably weaker acid than the carboxylic acid. So this being a weaker acid makes this a stronger base, all right? So we're starting to see a pretty poor leaving group, all right, in the OR minus, and we really need acid catalysis to get esters to react, all right? Whereas anhydrides and acid chlorides do not need acid catalysis to react in nucleophilic addition elimination reactions. All right, so in the case of the nitrogen leaving group, what we're going to see here is that guy as the leaving group, all right? So it's an N minus, and its conjugate acid is either a primary or secondary amine, and those have pKa values of around 35. So we can see that that is a considerably weak acid. Thus, it's going to have a very strong base as its conjugate base. So that is a terrible leaving group, all right? So of these four, the worst leaving group is on the amide. So this guy is going to be the least reactive, whereas the acid chloride is going to be the most reactive. So this should summarize our carboxylic acid derivatives that we're looking at, all right? And I'd like you to really study these leaving groups and understand why some leaving groups are good and some leaving groups are bad. And also it will tell us about the rates of our reactions and what kind of conditions we need these to react in. All right, well, thank you, and that'll do it for this video.